So welcome again to the University of Washington, to the first of a series of three lectures on astronomy. Astronomy is an amazing science. It is the oldest of the sciences, and in many respects, the newest of the sciences. As we probe the universe with new devices, new techniques, new brains, we are learning more every year pretty much than we have learned in all of previous history. So it's a very exciting time to be an astronomer and to participate in an event such as this. My name is Pinky Nelson. I'm Associate Vice Provost for Research here at the University of Washington and also an Associate Professor in the Astronomy Department. And it's my pleasure to host their series of three lectures. Tonight, the next lecture will be next Tuesday night at 7:30. Professor Bruce Margon will be speaking, and then a week from next Tuesday on the 7th of May, Professor Craig Hogan will be speaking, and we hope you can attend all three of these lectures. I want to thank a few people and organizations before we get started. First, the Computing and Communications group here at the University of Washington for putting together all this electronic marvels that you see and videotaping these lectures, which will be shown again on UWTV. And then I would also like to thank the News and Information branch at the university for helping to publicize and getting all of you folks to come out and listen. Finally, I want to thank President McCormick, who suggested that we give these lectures. President McCormick is an American historian who is an avid reader of Scientific American and suggested in reading about astronomy, the excitement he felt for the field, and wanted to have the researchers at the University of Washington share what we're doing with the public. And finally, I want to thank the Walker Ames Fund, who provided the funding for the videotaping and for the advertising in this. Tonight's speaker is Professor Don Brownlee. He is a professor of astronomy here at the University of Washington. He has a bachelor's degree in electrical engineering from University of California at Berkeley. His PhD is in astronomy from right here at the University of Washington. Don has a number of credits, and I'm only going to give a few in rank order. He is a member of the National Academy of Sciences. He has an asteroid named after him, 3259 Brownlee. Most importantly, he is the husband of Professor Paula Scody in our department, and he's the father of Allison and Carson, who are here in the audience. Tonight, Don is going to talk to us about everything old is new again, new comets, new stars, especially new planets. Don Brownlee.
Okay, I'm going to talk about planets, new planets. Planets are small bodies that orbit stars, and sort of by definition, they're too small for nuclear burning on their interior. On a cosmic scale, planets are small, cold, dark objects relative to stars and most of the other ingredients of the universe. Although attention to planets dominated the first 1,000 years or so, or first few thousand years of the astronomy field, planets are really insignificant members of the overall cosmos, and modern astronomy deals primarily with other things now, on grander scale and more distant objects and so forth. However, we should never forget that planets are very important, particularly to us. They're particularly important to us because they uniquely in the universe are a place for life. Life, as we know it, requires chemistry, and appropriate chemistry only happens in very special places. First slide, please. This is a very special place. It's very common around here, but it's an extraordinarily rare place on a cosmos or universal scale. I want to tell you right now about a fraud in astronomy. And during the other two lectures and other lectures in general in astronomy, you see a lot of really neat pictures. But these are really frauds in the sense that although they're interesting things, you know, black holes and galaxies and stars and so forth, they're just pretty pictures, you know. And as an armchair person, you might think, well, I'd like to think about going there. But it's not true. You would never want to go to almost any of these places you hear at astronomical lectures, ever. People always think, I'd like to go to the stars. But, you know, imagine if you went to a star, it's been 1,000 years getting there, when you got there, you'd be really disappointed. It wouldn't look any different than the sun. You'd turn around and come home, and you'd be kicking yourself all the way back home. Stars are dull. They're just piles of hydrogen and helium, you know. They're bright, but they look pretty from far away, but you get up close, you know, what the heck? You want to go to planets. I mean, going to a star is like going to the center of the Earth. You might like to think about it, but you really wouldn't want to seriously do it. Most places in the universe are too vacuous, or too dense, or too hot, or too cold. It's only planets that are really interesting. Planets are really great places, and they have some very important properties. One is at least some planets have temperatures, room temperature, that allows things like liquid water, Frost Pond here, to exist. Another very important property of planets is they have dense aggregations of material and surfaces. Surfaces are extremely important. Not all planets have surfaces. For instance, Jupiter doesn't have a surface, but we have a surface. Surfaces are very handy because you can rest on them. And if you want to create life, you can build on a surface. If you're in a star or in Jupiter and you're sitting there, you're not going to stay there very long unless you're hovering on an airplane or something. You've got to go up and go down. When you go up, it gets too cold. You go down, it gets too hot. So it's very important to have surfaces and also the right composition. And let me show you the composition of the cosmos. The cosmos is primarily made out of two rather nasty elements. Not nasty, but just boring. One of them is hydrogen. And to give you a feeling for what the cosmic abundances of the elements are, here's a slide with 15,000 hydrogen atoms. Now remember this proportions that are important here. So there's 15,000. These are just crummy, non-chemically interesting things. Just proton with electron around it if it's cold. And the cosmic abundance scale, here's another about 15,000 hydrogen atoms with the yellow dots up here. And this is helium in proportion. About 10% of the universe by number is helium. And you start getting down to these interesting things down here. Out of 30,000 hydrogen atoms, you have 10 carbon atoms, 3 nitrogen atoms, 25 oxygen atoms. The things that make out the Earth are the 3 dots at the end: iron, magnesium, and silicon. I have a piece of either hydrogen or helium in them here as a demo. I just said it's more interesting than hydrogen maybe, but it's still pretty dull. And I've had a technical breakdown. I was going to open this up, but I can't. So this may fail, but I'll try it.
This is helium.
I debated with our.
This is really helium.
I wanted to debate it with our chairman whether to do this. My wife said I was stupid to even try it, but anyway, I did it anyway, and I didn't collapse. So you see that coming out of that balloon? Very boring. 10% of the universe is made out of helium, and the rest is made out of hydrogen. Colorless gases that aren't very interesting. Now here in my pocket is a much more interesting material. This is basically the composition of the Earth. This is a rock. It's 4.5 billion years old, formed in the asteroid belt. It's a meteorite. And it's made out of those 3 atoms at the end, iron, magnesium, and silicon, in almost exactly equal proportions atomically, plus a little oxygen thrown in to form compounds. Anyway, planets, at least like the Earth, have the right composition. And not only do they have mostly iron, magnesium, and silicon, but they have a few other elements that are really interesting. And just for fun, I brought some of these elements. These 3 elements right here are responsible for our beloved Mount Rainier and the geology department, which is kind of fun. You might guess what they are. They're all radioactive as hell. This is potassium pills from Bartell's that people eat. This is almost pure thorium oxide. These are Coleman lantern mantles that you can buy in the grocery store. And this is an element that was discovered right after the planet Uranus was discovered. This is uranium. It's uranium glass. It's got a really neat fluorescent green color. But iron, magnesium, and silicon plus oxygen make up the bulk of the structure of the Earth. But these three elements, uranium, potassium, and thorium, were produced in stars older than, before the sun and planets existed. They're radioactive, and they are responsible for heat generated in the interior of the Earth. The sun heats the surface of the Earth, but the interior is heated by these three elements, uranium, potassium, and thorium, and that's what produced Mount Rainier. Without these three elements produced in early generations of stars, we'd have a geologically dead planet. So you can thank your lucky stars. There lives a little bit of these things. About a part per million of the surface of the Earth is uranium and these interesting elements. Okay, planets are great places, but until last year, the only planets known were our own, the 9 planets around the sun. For generations, people have speculated about planets outside the solar system. Are they rare? Are they common? Are we alone? There was reason to believe that there might not be any other planets around other stars in the universe. There's no theory that says when you form a star, you automatically form planets around it. So you can't rely strictly on theory. You have to observe. You have to rely on observations. But let me talk a little bit about theory. We know basically how stars and planetary systems might form. And we believe they form in a situation like this. This is actually the Sombrero Galaxy, but it's about like what the solar system looked like 4.5 billion years ago when it was forming. A gravitational collapse of mostly hydrogen and helium, plus a little bit of the heavier elements that the planets form from. And it's spinning, it collapses, forms a star on the inside, and forms a disk of stuff around the outside. The dark stuff here, in the case of the solar system, would have been ice and little rocky dust particles that the planetary bodies would have formed from. The idea for this was originally purported by Kant and Laplace, the so-called solar nebula. But it was an amazing process. You had something like this, and you had processes that occurred inside that are believed in general, but the details of these processes aren't fully known. You have solid particles settle down to a plane. They collide and stick and form bigger and bigger objects. There's sort of different pathways that lead to Earth-like planets, which are mostly rocky materials. And in the outer solar system, there was a slightly modified pathway that led to Jupiter-like planets. Jupiter-like planets first grew like the Earth, probably, and then accreted most of the hydrogen and helium that makes up the bulk of their mass. Jupiter is the biggest planet we know of in the solar system. It's 318 times more massive than the Sun. Anyway, we can't really predict that this process should occur around other stars. It might, but it might not. How does it really happen? We have to rely on observations. But planets are very difficult to observe. They're cold, and they're dark, and they're small. Very, very low mass. And they're very close to very massive things. Think of what the solar system really looks like. When you go out at night, look at the sky, and you look at, well, there's, Venus and Jupiter and so forth. That's what the solar system really looks like when you're actually inside of it. They're little tiny pinpoints of material. You all saw pictures of the solar system when you're in 3rd grade. There's a planet here, a planet there, and a planet there. But those are all frauds. You cannot draw a picture of the solar system and look at the actual scale because your eyes don't have enough resolving capability. The old story, if the sun is an orange, Jupiter is a pea, and it's over in the hub. And you just can't see those things on the same scale. So planets are very, very difficult to detect. And people have long thought about how you would do this. But fortunately, there have been great strides made very recently. And what kind of evidence might you have that planets might be common? I'll list it here, and then I'll talk about them individually. One are infrared excesses around stars that are observed. These aren't really planets, although in one case it may be, but they're evidence for planetary materials. Planetary materials are solids that have accreted to form larger objects of millimeter to maybe centimeter to maybe planetary size. And recently it's been possible to actually see disks of dust around some stars. Then there's a curious evidence from things like pulsar planets, brown dwarfs, which may or may not shed any light on this whole picture, but I threw it in anyway. And finally, Doppler detection of planets, which I'll talk about. Now, there are a lot of schemes now for detecting planets. There's a group at the University of Washington partially called the MACHO Project, which hopes to use gravitational lensing to detect planets. We now believe that planets are, in fact, common. And now people are really scrambling to find out ways to study them in great detail. It was like the Wright brothers. You know, once the Wright brothers showed that it was possible for people to fly, everybody started building airplanes. Partly it was technology, but most important, it was knowing that it's possible. And now we know that planets, extrasolar planets are possible. Everybody is getting into the act. Okay, one evidence for planetary materials, the so-called infrared excesses. I have a little demo of this, which you may not be able to see because it's so bright in here. But imagine this is a star. This would be really bright if all the lights were off in this room. But anyway, this is a star. It's a light bulb, but it's half the temperature of the surface of the sun. And if you look at the light from it, you see an energy distribution that looked like this. This red curve here is the intensity versus wavelength. This would be the visual range here. Then it would taper off as you went far out into the infrared. Now, if I take this light and put a bag over the top, this is a bag, but think of this as dust. This part's going to absorb some of this light. If I put the bag over the top of the light, what happens? Some of the light still comes through. And it's diminished a little bit, but it still has the shape of intensity versus color or wavelength at this bottom line. However, some of that light's absorbed. It heats up the bag, and the bag radiates. But the bag, because the bag is bigger, it has more surface area than the star, it radiates at a much lower temperature. And the bag may be quite far from the star. The star may have a temperature of 5,000 degrees on its surface, and the dust or bag may have a temperature of only 50 degrees above absolute zero. But still it radiates in the infrared. So when far away on the Earth, you use a telescope and you look at this object, you see this funny curve like this. You see the normal light emission peaking in the visual range that you expect for a star like this. Then you see this funny excess out here in the infrared, called an infrared excess. And what that is, the infrared excess, is from this heated dust surrounded by the star. Even though the dust may be very cold, it's still emitting in the infrared, and it's peaking out here at wavelengths like 10 or 20 microns, whereas the star is peaking out here, say, in the yellow region, in the visual range. Anyway, this is seen in many young stars and some old stars, and it's evidence for at least dust around. In some cases, the dust is just left over from formation of the star. In other cases, it's direct evidence of planetary materials. This is the most famous case. This is a star called Betapictoris, which was found to have an infrared excess. 0.1% of the light that's emitted by Betapictoris is absorbed by dust around it, re-radiated in the infrared. By honing down techniques to look at it with ground-based telescopes, people were able to take this fabulous picture. The star is actually blocked out by a little disk in here. It's called a coronagraph. But you see this disk extending on both stars. That's spinning around an axis like this, and that's dust around the star. You can calculate that that dust should not survive for the age of the star around it, so something is making that dust. What's making the dust? Bigger objects. Comets, probably kilometer-sized, well, anyway, big comets, much larger than interstellar dust, which is tiny, tiny bits of dust, smaller than dust that collects on your kitchen countertops and so forth. And with the march of technology, this can be studied even better. And this is a better image of it. This is the star in the middle, and this is the disk around it, imaged by the Hubble Space Telescope, of which you'll be seeing a lot of spectacular pictures during this lecture series. Not only can you see it better, but you can see it's warped. And some people claim that this is evidence for a planet somewhere inside here warping that dust disk. Now you might think it's a bit curious looking at a picture like this. We're looking at a Betapictoris. We're looking for planets. We don't see planets, we see dust. Instead of seeing something that's thousands of kilometers in size, we're seeing light reflected by little teeny bits of matter that's microscopic in size. Why is that? That's because dust is a very sensitive indicator of other things around. And dust has a huge surface area for its mass. It enables you to see it. Just think of taking a grocery bag and filling it full of twigs, sticks, and sitting on top of the Space Needle, looking at it from campus. Could you see this bag of sticks? No way. You take the bag and burn it. Then you can see it, because when you burn it, at least part of the sticks are converted to smoke, which is submicron in size. And the sticks converted to smoke amplify their surface area for the given amount of mass, the mass that's just put in there, by a factor of 100,000 to 1,000,000. And you can easily see it. So you can send smoke signals over long distances where you couldn't use semaphore flags. So one indicator of these things is using very fine particles because in taking advantage of their very high surface area to mass ratio. Now, besides infrared excesses, another evidence for planetary, the planets might commonly form around stars has to do with observing young stars and disks that may be around them. Stars form in star-forming regions. They form in groups. They form at about the same time. And this is a very famous picture. In fact, I'm a little bit famous down in health science now, where it makes these slides for us. I send it down electronically, and when I arrive the next day to pick it up, it says, "Oh, you're the guy with the Eagle Nebula slide." And what this is a region where stars are forming. They're surrounded in this gas and dust, and you don't normally expect to see solar nebula or planetary nebula type processes forming because all the dust sort of obscures it. But it's a very interesting process that happens now. In this star-forming region, you have some hot stars up above here. The ultraviolet light from the stars photoablates off the cloud, driving away the gas, leaving little stars sticking up the clumps of these little things that look like algae plumes coming up. Part of the attraction of this slide, by the way, is their use of biological tone or colors for its rendition. But anyway, it's a fantastic slide. And in some of these star formations, very recently, this is the HST Hubble Space Telescope pictures from Odell in Texas. Some cases you can see newly formed stars with illuminating light behind it from a cloud of material behind it, and you're looking at it like a shadow, a profile. Here's a star, and you're seeing a disk, directly imaging a disk of dust, only a few solar system diameters in extent. And these are dust in disks around stars, and almost certainly when you have a situation like this, the dust collides, sticks, and makes bigger and bigger things. It rapidly goes from dust size to centimeter size to meter size to kilometer size. In many cases, it may go automatically to planets. Once you have a situation like this, you probably can't prevent the production of planets. Now, if this actually was a solar system and you could watch it forming, if you sat there for only a few million years, you would see the disk disappear and replaced by tiny specks of light, which would be the planets. It's a very fast process. 10 million years, you may think of as a long time, but it's not a long time compared to, say, the old age of the solar system or the age of the universe. Solar system is 4.55 billion years old. Okay, I'm not sure this is really strong evidence for planetary systems or not. Maybe it's just, anyway, it makes you feel comfortable that planets might be common. These are called brown dwarfs. And here's one that's imaged in 1994 from Palomar, and here's the brand A, brand B. This is the Hubble Space Telescope picture of the same thing. Anyway, this is the brown dwarf. Now, what is a brown dwarf? A brown dwarf is a star that's not a planet, but not really a star. In order to be a legitimate star, you have to have nuclear burning on the inside of converting hydrogen into helium. And the minimum mass for a star to do that is about 7% of mass of the sun. And so if you take hydrogen and helium and collapse it to form a star, and it ends up being less than that, then you've still got a star-like object, but it's not hot enough in the interior to have nuclear reactions to make hydrogen into helium, so it's not really a star. It's called a brown dwarf. This one is 20 times the mass, about 20 times the mass of Jupiter, so it's really not considered a planet. It's too massive to be a planet, but it's not massive enough to be a star. There's sort of a definition of brown dwarfs as being intermediate in mass between 6% or 7% of a solar mass and just massive enough to burn deuterium, which is the rare isotope of hydrogen on the interior. Anyway, brown dwarfs have been predicted a long time ago. People searched for them carefully and only recently identified really good brown dwarf candidates. Now, how do you really detect real planets around stars? The straightforward way you would like to do this is just take a telescope and image the things. I'll talk about that at the end, but that's really difficult. For a century, it's been realized that you might be able to detect planets by their effect on the star that they orbit around. Think of this as the sun, and this is Jupiter. It's about the same scale, same size scale. But remember, the sun's here, Jupiter's over in the hub, so this is not drawn to that scale. Now, so Jupiter is 10 times is 1/10 the diameter of the sun, which means about a thousandth of the mass of the sun. And the balance point is right about the edge of the sun, right here. So this point right here, my finger, is the balance point. Now, you commonly think of Jupiter orbiting around the sun, but it's not really true. Jupiter and the sun orbit around the center of gravity of the Jupiter-Sun system. So when they rotate, you see the following thing like this. You see the sun wobbling there. So the trick is to detect that wobble. You can see the star from a long ways away. You can't see Jupiter because it's 1 billion times fainter than the star, and it's pretty close to it in the sky. But you want to detect this wobble, and that would be, if you could detect that and measure it, then you could calculate the mass of the object causing the wobble, and if it has a mass comparable to a planet, you might consider it to be a planet. So this is the approach. And how do you do it? Well, one way is to image the star and look for it wobbling around the sky. For Jupiter around the sun, image from a distance of 10 parsecs, which is an astronomical distance, which I'll let the later speakers define for you here. It's a couple light years. Anyway, the wobble is 10 to the minus 3 arc seconds, which is real small. An arc second is about the best resolution to get with nominally good telescopes. A 6-inch telescope will get 1 arc second resolution under really good seeing conditions. But anyway, 10 to the minus 3 arc seconds is really pushing the state of the art, and no one has succeeded with this technique yet. The other technique is to use the Doppler effect. So if you look in this plane, you look for the wobble. But ideally, if you look in this plane, you look for the Doppler effect. Now, what's the Doppler effect? A lot of you know what the Doppler effect is, but I want to make sure that everybody knows what the Doppler effect is. So I will try to have several cornball descriptions of the Doppler effect. You've all seen pictures, you've all seen people going through speed traps using radar. That's the Doppler effect. You've all seen them saying, well, Randy Johnson's pitch is 97 miles an hour. How is it determined? Doppler effect. Doppler effect is the shift of wavelength of something because of the motion of the object. So say if I was emitting a radiation with this wavelength, this is a slinky. I'm emitting this radiation. So if I start walking towards the audience in here, then you, the audience, would see this wavelength I'm emitting to be reduced, like this, as I walk forward. If I was going away from you, redshifted, this wavelength would be stretched out, like this. People over on the side wouldn't see anything unless we're going at relativistic speeds. Anyway, that's the Doppler shift. And how this is done is shown in this little cartoon in here. So this is, say, the sun going around the center, or the star going around the center of gravity of the sun and a planet way off in the side. So it's going around, that circular motion is the motion of this thing going around like that. And the figure of merit you want to try to approach is the sun moves around the center of gravity of the system at a speed of 12 meters per second. Very small. But the technique is to look at the spectra of the star, which is this spectrum right here. And the black lines are attached to the star. They're absorption lines in the star itself. And they shift around due to the motion of the stars. When the star is up here, it's coming towards you. And so the lines are shifted to the blue. And half a year later, for the planet that's orbiting around it, which in the case of Jupiter would be 6 years later, the light is shifted towards the red. And so the technique is you take the spectrum and then you have these reference lines. The reference lines are a fascinating case in science. When people first started doing spectroscopy, they'd take a spectrum of the object, they'd take the spectrograph off the telescope, put it in the basement or somewhere, and then use the reference lines from a lamp in the lab. It had huge errors, infinitely larger than what we're talking about here. But now the technique has been highly refined. What they do is they put a gas cell in front of the spectrograph in the telescope filled with iodine gas. And the iodine gas produces the absorption lines. And they measure the shift of the black lines from the star relative to the reference lines and calculate the velocity. And the velocity equals the wavelength shift divided by the wavelength times the speed of light. And it requires fantastic precision to measure it to the level to detect planets. But this has been really refined recently, and now the current state of the art is it is possible with these techniques to measure speeds of 3 meters per second. That's slower than a marathon runner goes for 26 miles. So it's a fantastically sensitive technique. We now have the power to tell whether there are planets around stars. And are there? And the answer is apparently so. But this is science. And you have to remember that science, there's discovery and data, and people will, interpret something one way, and then maybe later some people interpret it another way. This is in the question mark zone right now. It's not a matter of opinion. It's a matter of proving that the effect is due to a planet. In this case, it probably is. Around this star, 70 Virginis, there is a Doppler shift of amplitude of 200 meters to 300 meters a second, really high compared to the uncertainty in the measurement. And here it's stretched out from 1988 to 1986. This work is done by Marcy and Butler at the San Francisco State using the Lick 120-inch. And they had this program of observing 120 stars, and they were looking for Jupiters. And so they were collecting data and collecting data and collecting data. They were looking for Jupiters. It takes Jupiter 12 years to go around the sun. They were going to collect a bunch of data and look at it. All of a sudden, some people in Europe saw something like this, so they very quickly started looking at their data. Now they're turning up what appear to be planets all over the place. And planets have and they're finding planets with much shorter orbital times than it takes Jupiter to go around the sun, is the real difference. Anyway, this is one case of them. And this is the velocity versus time of the star going back and forth. It's either the star wobbling around the center of mass of a star planet, or the star is doing something weird, like pulsing on this time scale. And that's one of the contention points. And here's another, 47 Ursa Majoris. Now, there are actually about a dozen things which people believe are actually extrasolar planets now. And here's a list of a few. And important thing here is to look at them, and they're not at all like what we had expected. However, the sensitivity isn't as good as it will be later on. We're finding the big ones now that are closest to the stars. Where things like, say here's a 1 Jupiter mass planet that's 0.05 AU from the star. That's 20 times closer to the star than we are, than we are. 100 times closer than Jupiter is to the sun, which means over 1,000 degrees on the surface. These are very different. These are one of the amazing things is a apparent discovery of very massive planets very close to the stars. There are good reasons to think why Jupiter-like planets, very massive planets, can't form really close to stars. And so the idea is, well, if this is right, then the planets may have formed further out and come back in. But this will be hammered out in time. Then there's these two things here, PSR. These are pulsar planets. This works like it's a Doppler effect, but instead of using the shift of light, uses the frequency change of a clock. Pulsars are neutron stars. They're things with the mass of a star, but the size of King County. They're stars that have undergone explosions, collapsed down to incredible density, about 10 to the 15 grams per cubic centimeter. Anyway, they rotate rapidly. They have a radio beam that comes off that can be very precisely timed. And you can use the timing of this to detect Doppler motions, pretty much as was done analogous way to what is done with light for these stars up here. And that's sensitive for detecting very small planets. And these planets are much less than the mass of Jupiter, Earth, or even moon-sized masses with distances of a fraction to an astronomical unit or so. Remember, the astronomical unit is the distance between the Earth and the Sun, 150 million kilometers. But we can never think of these as being warm, fuzzy planetary systems. These are planets, these are things around neutron stars that had a violent history. So who knows what they were before their star went wacko. Anyway, there's abundant evidence, and finally I put Betapic down here because some people really think that there is a planet around Betapic that's warping that disk. We are the first, of the thousands of years that people have lived on this planet, we are the first ones, and only within the last year this has happened. We are the first ones that can now at least strongly believe on scientific evidence that planets are in fact common in the universe. So what's next? And NASA has a plan, not an approved plan, but an idea of a project called XNIPS, Exploration of Neighboring Planetary Systems. And by exploration, they don't mean sending off a starship to visit and come back. They mean just trying to detect these things. And so here's an idea that you can sort of think of in times. Direct detection of planets is occurring right now, as we speak. Last week, there was a thing in the paper about discovery of a new planet, and there are a couple more coming out soon. This is right now. On a time scale of 10 years, develop the capability to actually image Jupiters, and in 10 or 15 years, family portrait and spectroscopy, and off in the future, and this may be wishful thinking, actually image the things. Anyway, so how would you do this? One of them is building big interferometers in space, which on a 10 years time scale could do this sort of thing. This is an infrared image of our solar system, or imaginary one. There's Mercury, Venus, Earth, and Mars. And this is the spectrum of Jupiter. Not very interesting, but this is the spectrum of the Earth. And it shows absorption due to some interesting things. Show a better view of that. This is what the Earth looks like from space. You could see this from a long ways away if you had a big enough telescope. And this line alone would tell you that there is life on Earth. You don't have to see people walking around, forests being cut down and so forth, and look for freeways. This line does it. You look at the Earth, you see absorption by carbon dioxide. Well, that's okay. Mars has lots of carbon dioxide in the atmosphere. But this feature right here is ozone. Ozone is produced from oxygen. Our atmosphere is made primarily of oxygen and nitrogen, with 1% argon due to the radioactive decay of these potassium pills here. But those aren't very important. But the nitrogen-oxygen is put into the atmosphere by biological processes. And it has no right being there. Without life, it would not be there. Without life, you'd only see a CO2 atmosphere. Oxygen is put into the atmosphere by plants. And some of the oxygen is converted to ozone, which you can easily detect at a wavelength of 9 or 10 microns in the infrared from a very, very long ways away, if you have a good enough telescope. So there is hope, actually, to look for evidence of life on other planets using technology that will be available within the next decade. Quicker if you spend more money on it. But, okay, I want to switch gears here a little bit. For the TV time, how much time do I have? 10 minutes? 10 minutes, okay. I have to warn you that the TV part of this has to end abruptly at an hour. And that doesn't mean we have to disappear after an hour. If I don't run over time, we can stick around, and I have a little movie clip to show at the end. Anyway, another piece of this picture is really knowing how planetary systems form. And planets form from rocks. Most rocks that planets form from are things like comets. And this is a picture of a comet. This comet Donati over Paris in the 1800s. And I'm going to talk a little bit about comets in a project that we're doing at the University of Washington to learn about comets, because comets are the building blocks of our solar system, but they're also the building blocks of other solar systems. The reason there's a disk around Betapictoris probably is because there are comets around Betapictoris producing the dust. This is what a comet looks sort of up close and personal. This is Halley in 1986. This is the gas and dust coming off the nucleus. But we really want to get up really close. Not only do you want to get up close, you want to get a piece of the comet and bring it back to the Earth so we can study it in great detail. So there's a University of Washington project with a little bit of help from JPL up here in the dark red and Lockheed Martin. Actually, they do most of the work, but we're the base of it down here. And it's a project called Stardust. We chose this name because we liked it, but also because we have a song, an airline, and a casino, and all that stuff. And everybody has a feeling for Stardust and likes it. But anyway, this is a mission called Stardust. And the Stardust mission will launch from the Earth, or will all participants will be raking leaves somewhere. In February of 1999, this is the Earth's orbit, that's the Sun. This is the orbit of the comet Wild-2, spelled Wild 2, it's pronounced Wild-2. It's launched on a Delta rocket, and it goes out on this red line here, which is a 2-year trajectory. 2 years later, it comes back. The Earth has gone around the Sun twice. It comes back to the point where it's launched from. The spacecraft flies past the Earth, uses the gravitational swing by of the Earth to go out on this loop out here. It goes around the Sun another time. This is the asteroid belt out in this region. And the third time it goes out in the solar system, actually the comet comes in here and actually flies past it, a distance of 100 kilometers from the nucleus at a speed about 5.5 kilometers per second. We stick our hand out, grab dust, and head for home at that point. And this is how it's done. This is a spacecraft that's about life size on the screen, about 6 feet long. It weighs about 250 or 300 kilometers. It's in great contention now exactly how much this thing weighs. But anyway, it's a spacecraft. It goes to 100 kilometers from the nucleus, takes high-resolution pictures. It pops up a collector right here. This is a sample entry capsule that brings the sample back to the Earth. And the technology for doing this is using this weird material called silica aerogel. It's a microporous glass. It's 99% pore space. The structure is made out of 30 angstrom diameter silica particles. This is it's called frozen smoke, just like glass, except it doesn't weigh anything. It almost floats in the air. These are particles which are shot into the aerogel about 6 kilometers per second, and they produce these caret tracks. Each thing right here is a particle trapped in it. This is what the collector will look like when it comes back from the comet in 2006. This is a more highly magnified picture of a particle collected on Eureka, European Recoverable Carrier, in aerogel. Particle came in here at high speed, slowed down, and there's the particle right there. So that's the kind of technique that we're using. And that's a very exciting project. We're working very hard on it, and you can all come back in 2006 and hear the details of the results. or 2004. The pictures will be on the World Wide Web. I want to give you a brief tour of some neat planets, not only because they're neat pictures, but remember, those specks of light that people are seeing off around other stars, or they will be seeing around other stars, aren't just specks of light. They're fascinating places. Unlike stars, planets are very interesting, complicated things, just like people. And I'm going to show a couple of these slides. This is Venus, 450 degrees centigrade on the surface, hot enough to melt tin. This is a crater, a female crater. Everything on Venus is named after women, except for one. Maxwell Monte is a mountain. But they're all female features, and it's a fabulous place. Venus, something to worry about, same size as the Earth, same mass as the Earth, only 30% closer to the sun. It was completely resurfaced volcanically just a few hundred million years ago by some totally unknown process. This is another planet, and this is Mars. Old craters, scouring due to flow of liquid water or ice. The closest analog to this on Earth is the Channel Scablands in eastern Washington, where the Great Spokane floods at the end of the Ice Age came through and ripped through everything and produced these gouges. In this case, the water flowed downhill, vaporized, and went into the sky. Mars is 50% further from the sun than we are. It's a very cold place. It's sort of a permanent ice age, but there have been times in the past when it was more Earth-like. Every time there's evidence for actually falling rain and forming little tributaries on Mars. And this is Perkins Lane. No. For those of you who don't live in Seattle, Perkins Lane is doing this. This is a collapsed landslide area called Cantor Chasma on Mars, which is a wonderful area of landslides. Some of these substance regions are areas where water has come out from and flowed downhill and let the surface areas collapse. Anyway, it's a fascinating thing compared to stars. I won't say a negative thing about stars, but this is not a planet, but it's bigger than some planets. This is Io. It's the innermost large moon of Jupiter. It had 8 active volcanoes on it, spewing out sulfur dioxide and sulfur into the air. Here's one of them when the Voyager spacecraft flew by about 10 years ago. That actually is the color of it. Here's Europa, second Galilean satellite out from Jupiter. It's covered with ice. It probably has an ocean shortly under the surface, and there's actually a group of oceanographers and other people at the University of Washington that are fascinated with the concept of putting a probe or submarine or something into the subsurface ice looking for life, or evidence of life. This looks like drift ice. There are almost no craters on this object. It's a very young surface, and there's water with sunshine shining on it, and there may be a geothermal activity on the floor of it. Okay, thank you. This is a place you wouldn't want to go to, but it's fun to look at. This is Saturn. It's not a surface you could walk on. It's just gas. It would be fantastic to go visit the rings. The rings are made out of rocks. You could stand on some of them, and they're only about 10 meters thick and 100,000 kilometers across. A very thin thing. This is sort of an analog to how the planets formed. That was the sun. The planets from a disk of rocks and dust that orbited around it. Neptune. Again, you wouldn't want to go there, but it's great to look at. This is another gas giant. You might want to go here. This is Triton, moon of Neptune. You wouldn't want to stay there very long, though. Triton is on an orbit that's decaying, and it's going to hit the planet. But you might want to visit, and it has interesting frozen nitrogen frost on the surface that comes and goes with the seasons, which last a long time because of the orbital time around the sun. It also has little fumaroles or little puffs of gas coming up, and they're actually like chimney strokes going downwind in this object. The surface pressure is 1/millionth the surface pressure at the Earth, but there's still atmospheric phenomenon occurring on this thing at the edge of the planetary region of our solar system. So my second to last slide, and the overall conclusion from this talk is summarized by this equation. I've got to show one equation. This is a very simple equation. F sub p is much greater than 0. Most of you have probably heard of the Drake equation. The Drake equation is an equation used to try to estimate how common life is in the universe. And it's a whole bunch of things multiplied times each other. And one of the factors is f sub p, the fraction of stars that have planets. Until a year ago, I thought, and a bunch of other people thought, that f sub p might be very close to 0. There's abundant evidence now that suggests that it's much greater than 0, and in fact may be very reasonably close to 1, like half or a quarter or something like that. There's now at least evidence, if not, it's not proven yet, but it's evidence that planets may be a natural common part of star formation and that many stars have planetary systems around them. Then the last slide, and if that's true, you might actually think of this. There's always been a subculture of people that are fascinated by looking for signals. You really can't go to distant planets outside of our solar system, not with any technology we can imagine today. But you can at least listen. If there are planets there, there might be somewhere people sending signals to us. This is a far-fetched thing. But anyway, it's all activities related to planets, life in the solar system, looking for more life in our solar system, and also looking or even thinking about life around other solar systems is a wide open field. And things have radically changed just within the past year. I think that's the end of the television section of this, and so thank you very much. And, I do have a